Okay, hi everybody. This is going to be the recording that goes over the homework that you were supposed to have done since the last time we met. So we're going to begin with our two definitions of what is an empirical formula and what is a molecular formula. So the empirical formula is the smallest, the chemical compound that has the smallest whole number ratio of the atoms in that compound. In other words, it is the one that has already been reduced. A molecular formula indicates the exact number of each type of atom that makes up that compound. Sometimes they share the same empirical and molecular formula, but sometimes they do not. And so we're going to take a look at some of these examples. So for the first thing, I'm going to circle the formulas which are empirical formulas, meaning they can no longer be reduced. So CaCl2 cannot be reduced, but C2H6 can be reduced by a factor of 2. So I'm not going to circle that one. KMNO4 can be reduced, or cannot be reduced, excuse me. P3H10 cannot be reduced. Al2O3 cannot be reduced. Na2S2O3 cannot be reduced. H3PO4 cannot be reduced. And that makes up all of our empirical formulas. Okay, so the next part that we're going to get into is recognizing that a empirical formula is really just the reduced portion of a molecular formula, and we need to be able to understand what is the actual multiple by which it's been reduced. Okay, so for this next part, we are going to be identifying what the empirical formula is of those remaining molecular formulas. So let's take a look at that part right here. So we had molecular formulas, and let me make sure that I can write them all down. We had our molecular formulas were C2H6, H2O2, H2F2, C6H6, let's see here, C6H12O6, and C4H10. Those were our molecular formulas, and we recognize those by realizing that they can still be reduced. So I'm going to go ahead and form their empirical formulas by reducing each of them by their common factor. So C2H6 reduces to CH3, and the factor we reduced by was a factor of 2. H2O2 reduces to HO, and that again was a factor of 2 that we reduced it by. Same for H2F2, factor of 2, but C6H6 is reduced by a factor of 6. So we end up with CH, and the factor we reduced by, or the multiple, was 6. On C6H12O6, that is reduced to CH2O, and we reduced it by dividing by a factor of 6. And then the C4H10 could be reduced by dividing by 2, so we end up with C2H5, and the factor we reduced by was a multiple of 2. Okay, so now that we've got the idea that these two things are interwoven with each other, there's a little bit of sample calculations here which goes back over our steps that we take to make sure that we understand how to find the empirical formula from a percent composition, and that's what we're specifically looking at today. So I want to get it all on here. So here is our example. We're assuming that we have 100 grams of the compound, so we converted all percents into grams. And then the very next step is we are dividing each of our grams. So step 1 was this conversion to grams right here. Step 2 is when we are dividing by the molar mass. So this specific part is dividing by the molar mass, and this happens to be the molar mass of potassium, and this one is carbon, and of course this one is oxygen. So we're finding our moles. So we've completed step 1 and step 2, recognizing that the 0.73 moles of carbon is the smallest number of moles. So then this part is going to be our step 3, where we are dividing by the smallest number of moles. We're going to divide them by the smallest number of moles, so we come out with approximately 2 moles, 1 mole of carbon, and approximately 3 moles of oxygen. So our empirical formula for this compound comes out to K2CO3. Applying these, because remember, this forms our subscripts as long as they are numbers which are really close to whole numbers. If they are not, then we have to make sure that we multiply half integers, in other words 0.5s by 2, 0.33s by 3, and so on. So that is a good summary of what we have to do in our steps. And so the next part we're going to be going through is exactly how we're going to apply our steps. And so that is going to be what I work through right now. And as I go through, you can pause me at any time so you can write your notes and go over these, but that's exactly how I'm going to try to complete the rest of these calculations. Okay, so let's go ahead and get started. Step number 1, I am going to be changing my 83.7% to 83.7 grams of carbon, and I'm going to divide it by the molar mass of carbon, and then I'm going to do that for hydrogen, 16.3 grams of hydrogen, and divide by hydrogen's molar mass. Okay, so what I did is completed dividing by molar masses, and I got 6.97 moles and 16.14 moles. So this next step is the step where I divide by the smallest number of moles, which gave me a subscript of 1 and a subscript of 2.32, which was too much to round down for. So I'm going to multiply both of these by the factor of 3, giving me C3H7 for my possible outcome for my empirical formula. All right, I'm going to repeat this same set of steps for the nitrogen, hydrogen, and oxygen next. Okay, so for this next calculation, I took my grams and divided each of them by the molar masses. So 14 for nitrogen, 1.01 for hydrogen, and 16 for oxygen. Once I did that, I recognized that the moles of the nitrogen, the 2.5, was actually the smallest one, so I'm dividing each of these by the smallest number of moles, and I come out with 1.98, and 1.5, and it's the 1.5 that's telling me that I'm going to have to multiply by 2, since that is a half integer, so I end up with subscripts of 3, 4.96, and 2, which means that my formula is N2H5O3. All right, and we're going to go ahead and complete the next calculation as well. Okay, number 3 had some chromium, some sulfur, and some oxygen. Once I divided by each of those molar masses, I got 0.51 moles for the chromium, 0.76 moles for the sulfur, and 3.06 moles for the oxygen. And so my division is going to be of the smallest number of moles, so 0.51, leaving me subscripts of 1, 1.49, and 6. So that left me with having to multiply everything by 2. So I ended up with Cr2SO3O12. All right, so my next one is going to be number 4, and we'll take a look at how that comes out next. Okay, so for our next calculation, we had 63 grams of carbon, which came out to 5.25 moles of carbon, 11.92 grams of hydrogen, which came out to 11.80 moles of hydrogen, and 24.97 grams of fluorine, which came out to 1.31 moles of fluorine. Our smallest number of moles was 1.31, so dividing by each of those, I end up with subscripts of 4, 9, and 1, so I have C4H9, and it shouldn't have been O. Whoops, my bad, everybody. That should have actually been an F. I did do the calculations right, I just didn't put the right species there on the end. All right, one more calculation for us to work through. Okay, so we end up with MgSO3 as our result after we, step 1, divide by molar masses to find moles, and step 2, divide by the smallest number of moles, that was 0.96, and step 3 was where we got to stop because we ended up with 1, 1, and 2.99, which was pretty much 3. So we ended up with MgSO3. All right, so our next part is recognizing that molecular formulas are really just a whole number multiple of an empirical formula. And so that way, if we can recognize that they're really just different by a certain multiple, then we can use their molar masses, empirical molar mass versus molecular molar mass, to determine what that factor is. And so this particular part right in here, the mass of the molecular formula minus or divided by the mass of the empirical formula, when we calculate that up, that is going to give us the factor by which the empirical formula can be multiplied to get the molecular formula. So here in this sample problem, our compound has an empirical formula of C2H4O, and it's told that its molar mass was 176 grams per mole. This is of the molecular formula. All right. So if that's the case, and then we want to know what is the molecular formula. So if this is the mass of the molecular formula, so the big one, then this must be the mass of the empirical formula. And now how did we get that mass of the empirical formula? Well, if the empirical formula is C2H4O, C2H4O adds up to 2 times 12 plus 4 times 1 plus 16. So atomic masses all added up, so that's 24 plus 4 makes 28. Plus 16, that actually does equal that 44 right there. When we do the math of the molecular formula divided by the mass of the empirical formula, we get a factor of 4. And when we multiply C2H4O times 4, we end up with C8H16O4. And this is our molecular formula. All right, so this next section is going to be all about how are we going to find the molecular formulas, and we're going to practice doing that in this next section. Okay, so I have done the first one so we can take a look at it here. On this, I'm calculating the molar mass of the empirical formula. Here's our empirical formula, P2O5. That's our empirical formula, and so I'm going to do 2 times the atomic mass of phosphorus plus 5 times the atomic mass of oxygen, which gives me 141.94. To find the factor, I am going to divide the molar mass of the molecular formula divided by the molar mass of the empirical formula, and I find out that the factor is 2. So I'm going to multiply the 2 times the empirical formula, which was this number right here, and that's going to give me P4O10, and that's my molecular formula. I'm going to repeat the same thing, but I'm going to do it with NH2 this time, and I'm going to find the molar mass of the empirical formula first. So I have 1 nitrogen, and that is 14.01, plus 2 hydrogens, which is 2 times 1.01. So I'm going to add those 2 together, and I end up with 16.03 for my empirical formula mass. And I'm going to divide that by 32 divided by 16.03, which gives me approximately 2 again. Now, that number is not always going to be 2, but this time it comes out that way. So I'm going to do 2 times NH2 gives me N2H4 for my molecular formula. I'm going to go ahead and continue that same thing for the next one. I've got 3 times 12.01. plus 5 times 1.01 plus 2 times 16. And so when I do my math, I am going to come out with 73.08. And so dividing by that, I end up with 73.08. And looks like all of my examples so far have come out to approximately 2 for my factor, and this one comes out to that again. So my empirical formula is 2 or was C3H5O2, and multiplying that by a factor of 2 gives me C6H10O4 for my molecular formula. So let's go ahead and try one that does not come out to a factor of 2. So let's look at CH2O. So I'm going to add 12.01 plus 2 times 1.01 plus 16 to find that my empirical molar mass comes out to 30.03. Whoops, I wrote 04. Hold on. 30.03. Now I'm going to divide 120 by 30.03, which is going to come out to approximately 4. So that means my factor this time is a factor of 4, and I'm going to multiply that by the molecular formula CH2O, so I end up with C4H8O4. And you can see how this continues. I'm going to go ahead and complete these two other calculations so that you can see them and how they work out. Okay, and to figure out, and greatness. We got that little technical difficulty out of the way, and so I went ahead and finished out the last two calculations, which ended up having a factor of 3 to multiply by and then a factor of 2 to multiply by. Hopefully this has been helpful to you.